First one or two. Yeah, they are.
I know.
Hey, where's that attendance sheet at?
But making it round, make it round. Okay, let's get started here, everybody. All right, as we get started today, I want to remind you of our earlier talk about atomic bombs. And I've redid this a little bit. This bomb right here, 10 feet long, 9,700 pounds, 1 10-foot bomb, we kill 100,000 people when it drops. The next one was even more powerful. We kill another 100,000 people instantly. This is not a nuclear warhead. Putin has now put his nuclear weapons on alert. You have to realize what is going on here. Never in my lifetime did I ever think I would see a country surrounded and invaded from 3 sides, like September 1st, 1939, when Germany went into Poland. Never in my lifetime. I'm watching a war live of a full-out invasion. I'm just stunned that Putin even made that announcement, because if nuclear war breaks out, we're dead, because they're going to take Eau Claire out. But we have 1,200 nuclear warheads in the submarine. So if they get to jump on us, we can obliterate them back. And then life starts over out in the country, basically, because all the city people are dead. So it's an interesting time. Please, please, please keep track of what is happening in the world. Okay. I should be sharing the correct screen now, I think. All right, as a review, since you're doing this for lab this week, let's do this second one. Let's do letter B here quick. On this one, got I'm on page 7. But you'll find it here like this. So on the test, which is 1 week from today, the only reference you're going to have is I'm going to give you this reference. I will give you this reference. Now I checked labs. It was a different class. It was different, and they thought there was 100 grams in a kilogram. So you need to know those metric prefixes, and then we went over these. So I'll make sure it just includes these ions. Okay, so for this, we have iron 3 chloride, which we can look up here for chlorides. And it says this, all chlorides and iodide salts are soluble except lead, silver, and mercury. And we've got iron. So we know this is going to be aqueous. We know this potassium compound is going to be aqueous. So when we first write this out as a molecular equation, we're going to have FeCl3 aqueous. plus KOH aqueous. And iron is going to take the place of potassium. So iron takes the place of potassium. This is +3 - 1. So the first mistake students make is there's not a parenthesis around hydroxide. And I'll just leave that blank. Plus, if potassium takes the place of iron, KCl. And we know that that is aqueous. Now, the question is this a precipitator or solid? Look at your solubility chart. Do you get a precipitator or solid here for hydroxides? And for sure we do, right? Because in order for hydroxides to be soluble, this should be sodium, potassium, ammonia. This is a solid. We'd have to balance this. There's 3 OHs, 1 OH, we put a 3 here. And that makes 3 metal potassiums, we'd have to put a 3 here. That would be balanced. So that is only a complete molecular. Now be aware as you're starting to review things, I believe on the quiz, I have used this terminology. This is the complete molecular equation. Or just molecular would be fine. Then there's a complete ionic. What is a complete ionic? Everything here splits up into ions, right? So let's do that quick. If everything splits up into ions. Now here is where, when you are doing lab, this is what I see. I see no charges here. Or then they go 3 Cl without a charge. If you do not put ion charges in here, it's completely wrong. There's no such thing. This then would be a Cl- atom with no charge. If you do not put these ion charges in there, you are not doing it correctly. Everything, if you have an ion, you need to have the charges in here. Then we would keep our hydroxide together. Complete ionic, right? Again, if you don't have any charges in here for the ions, it's completely wrong. We're assuming that you're writing, assuming that you're writing compounds. So now we can pick out the spectator ions, right? So spectator ions in here, what is the same on both sides is 3K plus, 3K plus, and three chlorides, right? And if we X those out with a light X, we should be left with a net ionic. Now I'm going to say it for about the 5th or 6th time. If you do not have ion charges here for these ions, it is completely wrong. We're assuming that you're writing iron metal, a hunk of 0 charge metal. In here, if you just have OH, we're assuming you have an OH compound. So make sure you're putting ion charges in. I would encourage you perhaps before you scan your lab into the instructor that maybe you go to room 426 and look it over there in the lab. If you want to improve your lab scores. Okay, let's see. There is not always a reaction here, by the way, because I'm pretty sure. I have an example on here that's no reaction. Is it that one? I think it's this one. But this you've probably been working on in hours. All right, let's review what we talked about last time. So, we talked a little bit about acids and bases here, and then we do pH later. Not my choice of the organization, but that is what it is. I'm going to bring up the right one. Remember, if you're writing out net ionic reactions, and if you form a weak acid, it has to stay together. And naming acids, we talked about strong acids, strong bases. Remember, you want to memorize these three: HCl, HBr, and HI. Then, what is Keyes' rule? I don't know if this exists anywhere else. If you have 2 or more oxygens, then hydrogen is a strong acid. And this has, 2 more oxygen than hydrogen, right? Nitric acid. This is perchloric acid. You have 3 more oxygen than hydrogen, and this you have 2 more oxygen than hydrogen. Then we have strong bases. What are strong bases? Group 1 hydroxides, lithium, sodium, potassium, rubidium, cesium would be included here. And group 2. And then what does it mean to have a strong acid? 100% of these hydrogens are going to come off, right? And they're going to leave their electron behind. The hydrogen electron is left behind. That's how we always get a negative ion. These bases are going to dissociate. We use the word ionize here because it's going to be plus H2O. And over here, we just say they dissolve or split up. If you have a strong base, what are you getting? Lots of hydroxide. Then if we have weak acids, we say that probably less than 5% of those hydrogens come off. You get few ions in solution, weak electrolytes, strong electrolytes. Strong electrolytes, lots of ions in solution. Here we have a weak base, weak electrolyte. So that's lab this week. Okay. Then we talked about Bronsted-Lowry. An acid is any substance that donates a proton. And we left off. We actually looked at that last time we met. And again, if you have a strong acid, such as HCl, HBr, or HI, this black dot is hydrogen's single electron. If this hydrogen comes off, ionizes, this hydrogen is only going to be a single proton. That single positive proton is going to be looking for some negative charge to bond to. Where does it find it? Right here. Water has 2 pairs of non-bonded electrons. That H plus comes off, it bonds to one of those pairs of electrons. So instead of, this is neutral, 0 charge, 0 charge. These are just neutral compounds. Over here, we get H3O plus. This is my H3O plus, hydronium ion. Why do we always end up with a single negative ion? Because hydrogen leaves its electron behind and it's right there with the negative ion. Okay, so we always get a positive ion and a negative ion. Now, what does Al do? The cheater way to do this reaction is to simply do this. They'll have HCl and they'll go H plus and they'll go Cl minus in aqueous. That is not really what happens. That's the old way to do it, but realize H plus really means H3O plus. Okay, it's just a shorthand way to do it. Okay, then we talked about weak acids. What do we know about weak acids? This hydrogen is not going to ionize or come off, or it comes off to a low extent. The amount of hydrogens that come off for a weak acid is unique to that weak acid. They're a pain in the butt because you have to look on the chart to basically see how many come off. They are all different because the negative ion is pulling on that positive hydrogen and the pull is different. You know you have a weak acid or base when you see a double arrow. This is an equilibrium. This reaction goes back and forth. The H plus comes off of the H3O plus, attaches itself to the F minus. You get water and you get hydrofluoric acid. That's the reverse reaction. At the same time, HF is coming off, or H is coming off of the F and it's bonding to the water to get the right side. So again, remember, if you have an equilibrium, the forward reaction and the reverse reaction keep going. The net effect is, though, these concentration, in this case, the concentration of H3O plus is going to remain the same. And then you would measure the pH. Okay, then a base is a substance that accepts an H plus. The most common weak base is ammonia, NH3. And remember, for this freak, it's this, NH3. -3 plus 1 on that, -3 plus 1. And when I write bases, if I know I'm going to get a base, I have to get OH minus. I'm going to write it as HOH. You're going to see me write instead of H2O. If I know I'm going to get OH minus, I know I've got a base, I'm going to write HOH. It really signifies that this H is going to come off of the water. Water acts as an acid. So strong acids, again, 100%. We use the term 100% ionized if you have a strong acid. Okay, so we left off here. And I think Al does a little bit of this. So we know H2SO4 is a strong acid. It's called a diprotic acid because you have two hydrogens. H3PO4 is a triprotic acid because you have three hydrogens there, right? Now it says the first ionization of H2SO4 is 100%. The second ionization is way, way, way less. So it says write the first ionization of H2SO4. So we have H2SO4 aqueous. The term ionization means plus H2O, liquid. And we know that this is going to go 100%. If one of these hydrogens comes off, we for sure, and one hydrogen is going to come off, we're going to get H3O plus aqueous. And the negative ion that is left, if a hydrogen comes off, is going to be HSO4 minus. This is your battery acid, sulfuric acid. Or you could be crazy enough to buy this as drain from at Menards. It's gonna be sealed in a plastic bag. I can't believe you sell it. Don't buy it. Remember, don't unplug your drains with harsh chemicals. Okay, then it says write the second ionization. Well, this is still an acid right there. So the second ionization goes like this. We're going to start with that, HSO4 minus plus H2O liquid. This is a weak acid. If it's a weak acid, there's double arrows. But we still get some H3O plus. And what are we going to be left with? If we take an H plus off of here, we're going to be left with SO4 2 minus. Okay, the most common weak acid is vinegar, just acetic acid. And for acetic acid, the hydrogen is, we could write it this way or this way. It's the same, but that's the hydrogen that ionizes. If we write it this way, it's going to be this one. If we write it more towards organic chemistry, it's going to be this one. So write the ionization reaction for acetic acid. So let's use, we'll use the second one. Al likes to use this one. So we would go CH3 COOH. It's still a water solution. H2O liquid. If we have a weak acid, we're going to have double arrows. And we are going to get, we always get H3O plus. And the negative ion left over is going to be acetate. CH3COO minus in this case. Now, the most common weak base is ammonia, which has the formula NH3. If you know you have a base, it is a good idea to write water as HOH. So write the ionization reaction for ammonia. The term ionization, it's really, you're going to add plus H2O to it. So if we do ammonia, we have NH3, it is in a water solution, plus HOH liquid. If you know you're going to get a base, write water as HOH. In OWL, you probably cannot type it in that way. You're going to have to type in H2O, but you should always be thinking HOH. This is a weak base, so we got to have double equilibrium arrows. And anytime you're making a base, think of water is acting as an acid, and H plus comes off. So, and 9 times out of 10, that H plus is going to attach to a nitrogen. So we can have this very ugly looking compound like this. Doesn't matter, we have a nitrogen. This is an OWL problem. So we are going to get NH4 plus aqueous, and we got to get OH minus if we have a base. So let's look at this owl problem then. So this is directly out of owl. So, well, I'm missing a T there. The substance aniline is a weak nitrogenous base like ammonia. Complete the following equation that shows how aniline reacts when dissolved in water. So we are going to get again, I'm thinking HOH, even though I have to type it in this way. And notice that this hydrogen is attached, this H plus as a proton is attached to the nitrogen. And what am I going to be left with then? If you're making a base, you have to get OH minus, right? Double arrows, right? Double arrows. So this is an example of an out question. Well, this is an out question. Again, if it's acting as a base, you better get OH minus, right? Okay. If we have a neutralization reaction, we typically have an acid plus a base, and we get a salt and water. So consider what happens when a typical antacid, such as melt of magnesia, and aqueous suspension of the solid magnesium hydroxide. If you have Tums, you would also have calcium hydroxide in there. To ease the symptoms associated with excess stomach acid, which is just HCl. So in your stomach, you have a buffered stomach system that has a low pH of hydrochloric acid, HCl, magnesium hydroxide. You still do double replacement on this. So hydrogen takes the place of magnesium. You could look at that then as HOH here. And then here's one, hydrochloric acid. So this could be the works toilet bowl cleaner, which is hydrochloric acid. This would be lye to unplug your drain. So you have a wicked acid. You have a wicked base. If you neutralize them, you can drink it, right? Because you just have salt water, which is what you should be able to accomplish. So if you added the exact correct amounts of each, you would have perfectly harmless salt water. Again, we look at it this way. Now this, strong acid, right? Strong acid, strong base. If you really did the complete ionic reaction for this, it would look like this. And then if we did our spectator ions, Sodium. Sodium. Chloride, chloride. What are we left with? H3O plus OH minus, we just make two waters. Now, the other cheater's way to do this is simply going to be H plus aqueous, OH minus aqueous. If you're neutralizing it, you're making harmless water, right? Neutral water. Okay. Make water. Now, your book goes into some reactions now. If we are going to make an acid, non-metal oxides, a YO, can form acids. So this is a generic reaction. If you have a non-metal oxide, a non-metal with oxide, carbon, sulfur, nitrogen, phosphorus, non-metal. You add water, you're going to get an acid. An example is carbon dioxide, water, you get carbonic acid. This is acid rain, by the way. If you have sulfur dioxide in the air, you have nitrogen dioxide. This is catalytic converters in your car that try to prevent some of this stuff from happening. So, non-metal oxides in water form acids. Here's another example on the next page, which is sulfur trioxide. But metal oxides form bases. So here's a metal oxide plus water, we get a base. Example, calcium hydroxide, sodium oxide. And if we have a base, we get hydroxide, right? Okay, here's a final summary. Acids. We know we have an acid. It's going to start with hydrogen, right? A generic might be HA for an acid. Hydrogen with some negative ion. Acids will produce H3O plus, hydronium ion, or H plus, hydrogen ions, or a proton. Bases will produce OH minus hydroxide. Strong acids, ionize. The term ionize, put in plus H2O, 100%. One-way arrow, correct? So you're just going to have a one-way arrow for these, not an equilibrium. Weak acids typically ionize, plus H2O, less than 5%. Every weak acid is different because the pull from the positive proton, the hydrogen, and the negative ion is different for every weak acid. So this percent is different for every weak acid. And that's going to be signified by equilibrium. But you're going to produce H3O plus, right? Strong bases, metal hydroxides dissociate. So we don't use the term ionize, simply split them up. Weak base, metal hydroxides dissociate way less. So an example of a weak base hydroxide could be like aluminum hydroxide. Weak bases typically ionize plus H2O very little. Again, less than 5%. Okay, some examples. Write balanced chemical equations for the acid-base reactions described here. Ionization of nitric acid. Is this a strong acid? Yes, you have 2 more oxygens than hydrogens. All right, so we can write that. We're going to have HNO3, aqueous, plus H2O liquid, one-way arrow. We're going to get H3O plus, and we are going to end up with NO3 minus aqueous. Ionization of nitrous acid. Is this a strong acid?
No.
No, because you only have 1 more oxygen than hydrogen. Therefore, it's weak. We're going to have double arrows then, right? So we are going to have HNO2 aqueous plus H2O liquid, an equilibrium situation with double arrows. And we are going to get H3O plus aqueous and NO2 minus aqueous. Now, dissociation of strontium hydroxide. Is this a strong or weak base? Group 1, group 2. This is group 2 strontium. This is a strong base, which means it's going to dissociate 100%. So we are going to have, let's see, if we could put this in as a one-way arrow. Typically looks like this. And that is going to split up into SR2 plus aqueous and 2 OH minus. This comes back to what all is going to look like for a weak base. Methylamine. So this is a weak base. So we're going to have CH3 NH2. And this is going to be aqueous plus, I'm going to write HOH. Owl probably is not going to like that. So you're going to have to put it in as H2O. I should try HOH in there. I haven't tried it. If this is a weak base, we know we got to get OH minus. H plus, water acts as an acid. H plus is going to come off, attach itself to a nitrogen. So remember, H plus is a positive charge. So we would get CH3 NH3 plus OH minus. Okay. Section 3.7, we've got two things to cover yet. Gas forming reactions and oxidation reduction reactions. So, gas forming reactions. And if we get a gas, right here is our gas. So all of these reactions are going to produce a gas somewhere. And I'll cover some of these. So it says metal carbonates and metal bicarbonates. So remember, X is just a metal. CO3 is carbonate. HCl3 is bicarbonate. So metal carbonates and metal bicarbonates react with acids, just HY for a generic acid, to produce a salt XY plus carbon dioxide gas plus water. So here is what a generic reaction looks like. So you should be able to follow this. We have a metal carbonate plus an acid. Look what happens. The positive ion here of the acid, excuse me, of the carbonate attaches itself to the negative ion of the acid. So we get XY. The rest of it's just given, CO2 plus H2O. And it's the same thing for the metal bicarbonate. So here is the table from the textbook. 3.2 gives us an example. So we have sodium carbonate plus hydrochloric acid. So let's take a color. This is my X. This is my Y, right? So a metal carbonate. My X and my Y. Okay, then we have metal sulfites. React with acids to produce a salt. Instead of carbon dioxide gas, we get sulfur dioxide gas and water. So very similar generic reaction. This, again, X is a metal. So we'd have X SO3, a sulfite. This sulfite is SO3, -2. An acid, we get XY plus SO2 plus H2O. Again, this is table 3.2 in the textbook. So there's an example here. there's my X. Here's my Y. And these are called gas forming reactions because, again, you get a gas. Then we have metal sulfides react with acids to produce a hydrogen sulfide gas. And this is a generic reaction. Metal. So these are the last 3 questions on the quiz, and you match up the correct equation for those. These are the last 3 questions on the quiz. Okay, and this is an ugly owl question, so let's see if we can tackle this. Everybody has this one, right? Okay. Well, then we'll be left next time we meet. We're only going to have to do oxidation reduction, which is section 3.8 and some reactions. Okay. So now this barium carbonate, notice it says it's a solid. This solid is going to get attacked by a strong acid. So let's, boy, they want a net ionic. Let's just write the reaction out first. So let's go up here and write this reaction out up here first. So we have barium carbonate. Plus nitric acid. So what's my X and what's my Y? Barium is going to end up with the negative ion of the acid. Well, there's my XY. So we're going to end up with barium nitrate plus CO2 gas plus H2O liquid. It's just a given. Is barium nitrate aqueous? Yeah, barium nitrate should be aqueous and nitrate. So now this is the molecular, right? My complete ionic is going to be barium carbonate. Al is going to write HNO3 as H plus aqueous plus NO3 minus aqueous. And then Ba2 plus aqueous, 2 NO3 minus aqueous, plus CO2 gas stays together, plus H2O liquid. So the only spectator ion I have out of that is this. And if we cross that out, we're going to end up with barium carbonate solid. Ooh, I didn't balance this. I need to put a 2 here. 2, 2, and 2 plus 2H plus. And I'm going to end up with Va2 plus aqueous. CO2 gas, H2O liquid. I think that's what we're looking at for that one. Okay, you can try the rest of the quiz except for you'll know if it says, well, you can't. You can do a few more in the quiz. It says oxidation reduction, though, so try the last 3 in the quiz. The last 3 in the quiz.